Another thing that we're going to introduce is the idea of the difference between a static system and a dynamic system. And so this is sort of to go along again with models of different levels of complexity. So a static system, the output is determined only by the current input and it reacts instantaneously. So for example, if this is our system and I give it an input of 2, the output will change to 10 instantaneously, and whenever I put a 2 into the system I will always get a 10 out. And so the relationship between the input and the output does not change, it's static. Every time I put in a 2, I always get out a 10. Furthermore, this relationship can be represented by an algebraic equation. So in this case you could model the system as multiplication by 5. You put 2 in, the system multiplies that by 5 to get an output of 10. Some systems are well modeled by this sort of static model, but many aren't. So for example, let's think of this as being a motor. And we apply 2 volts into the motor. In reality, the speed of the motor wouldn't instantaneously jump to 10 radians per second. It would take some time to sort of spin up. So a dynamic system, or a dynamic model of a system, the output takes time to react. Furthermore, the relationship between the input and the output changes. It's not always the same. If I put in 2 volts, the output isn't always 10. It depends on how long has that 2 volts been applied. It depends what was the speed of the motor before I applied the 10 volts. Was it at rest or was it already spinning? So the relationship between the input and the output changes. It's dynamic. Therefore, we can't represent the system by an algebraic equation. We need to represent it by a differential equation, meaning that we need to represent it by an equation with derivatives. So let's take a look at a motor from a model of a motor from a static viewpoint and from a dynamic viewpoint. And so one way to look at a model of a motor is as a torque speed curve. And so if we look at this, we have some voltage input to the motor, EA1, and we have some load torque. We'll get some, if we look at this table or we look at this graph, we get some corresponding speed. If we change the load, we jump down to a different speed. Or if we change the voltage input to the motor from EA1 to EA2, we also get a different speed. And so this in essence is a static model. You change the input, you change the conditions, the output changes instantaneously. It doesn't capture the dynamics. In reality, that's not how a motor works. In reality, if you change the load or you change the voltage input to the motor, it will take time for the motor to react. And so in reality, we'll get something like this, where it takes time for the motor speed to ramp up, or the torque of the motor will take time to change. What then is this torque speed curve capturing? In reality, what it's capturing is it's sort of capturing the steady state behavior of the system. So for a given voltage and a given load torque, this is what the speed would be once the transients die out, once we sort of reach steady state. These two types of models are both valid. It just sort of depends on what your goal is, or what you need from it. So the torque speed curve, it's very simple. It's very easy to solve. You just look up the graph or look up a value in a table. So it's very simple to solve, but you lose the transient behavior of the motor, which could be okay depending on your situation. So if you're just trying to perhaps size the motor and you want to know what the maximum speed is or the maximum torque is, this could be fine. Or if you're going to operate the motor in in a way that the conditions don't change very quickly, then a torque speed curve may be sufficient. But if you're interested in understanding these transients, you want to know how fast does the motor take to respond, then you need this dynamic model, which will be more complicated, i.e. it will be a differential equation, which is harder to solve but gives you more information. So this is a common trade-off that we will see between sort of usability of the model, ease of use of the model, and level of accuracy. To summarize what we've covered here in Module 2, introducing the topic of modeling, we looked at a couple of different approaches to deriving models, one being from first principles, using physical laws like F equals ma, another being a black box approach, where we feed a known input, observe the output, and try and match the two. And so we talked about sort of what some of the advantages and disadvantages of these two approaches are. How much intuition do they provide? How easy are they to generate? What do you need to know? How widely applicable are these types of models? We've also talked about the level of detail to include in a model. So the level of detail depends on what you need it for. What kind of questions are you trying to answer? Under what sort of conditions do you need the model to be accurate? What level of accuracy do you need? There's trade-offs between the complexity of the model and the accuracy, the speed with which a simulation could run, etc. And along these ideas of complexity trade-offs, we looked at what the difference between a static model is and a dynamic model is. The level of accuracy that you get, does it capture the transient behavior? Does it only capture the steady state behavior? How easy is it to use? Is it an algebraic equation or a lookup table that's very easy to solve? Or is it a differential equation that's more challenging to solve?